Welcome back to Chapter 18. We are picking up with Video 3, and we'll talk about conduction and induction. They are two ways you can charge items. So, in order to discuss them, we need to have some ground rules. The first rule is only electrons move. So even though in our drawing you'll see positive charges, the positive charges will not move. They're trapped inside the nucleus. So they are not mobile in these examples. The second rule is that like charges will repel and unlikes attract. We've used that recently, and it'll come up in these examples. And the last is that charge is conserved. And again, you're familiar with that. We don't create or destroy charge. We just redistribute it. So let's look at charge by conduction. We'll start out with charge by conduction. Oh, I overshot again. I apologize. I am not as good at this as I would like to be. All right, so charge by conduction, that requires that you take your object and actually you have an object you want to charge and you have a charged object. And charge by conduction means the two have to physically touch each other. So in this drawing in figure 7, we have a negatively charged rod. That's what this is. And we have a neutral, it looks like a can, so it could be a cylinder. You'll see that the reason I say it's electrically neutral is it has the same number of positive as negative charges drawn on it. The rod, while it has some positive charges, has many more negatives. So it's a negatively charged rod because there's an excess of negative charge, and the cylinder that we're looking at is neutral. When the two physically touch each other, there's an effort for charges on the negatively charged rod to move away from each other, because we've already said that only electrons move, so the protons are trapped, and that like charges repel. So the electrons are going to try to move away from each other on the rod, and some of them will move over to the electrically neutral cylinder. If you took this rod away, the end result would be that the rod would still be negative, it just wouldn't be as negative, and the cylinder that started out electrically neutral would end up with a negative charge. So it's charge by conduction. It produces like charging. That means if the charging object, the rod in this case, is positive, the cylinder will end up being positive. It'll end up actually, the charged positive objects end up taking electrons away. Negative objects end up donating charge. So charge by conduction requires touching, and it produces like charging. So a charged positive rod will give you a positive object. Negative rod will produce a negative object. And again, our rule is only electrons move. Charge by induction is a little different. To have charge by induction, you have a charged object. So in this case, again, a rod. Here we have a negatively charged rod, and it doesn't show any positives, but they're there. They're just not very many of them compared to the number of negatives. And then you have an electrically neutral, in this case, metal sphere. Again, same number of negatives as positives. For charge by induction, the charged rod does not touch the object, all right? But instead, you touch the neutral object with something that grounds it. It could be a wire connected to the earth. That's what a grounding wire does. It physically connects your object to the earth in some way. Or I could have somebody standing there touching the rod. So if you want to ground something out, you can touch it with your finger. That means you will either donate electrons if they're needed, or you'll accept extra ones if they need to get away. So in this instance, what happens? If you have the negative rod and you bring it close, it will certainly attract positive charges, but they can't jump the gap. They don't move. They're trapped in the nucleus. So it's the negative charges that do the moving. Negative charges will actually be repelled by the negative rod, and they will go along the exit route you've provided with the grounding wire. If you were touching it with your finger would be the grounding object, and it would carry extra negative charges away. The end result is that it would leave a net excess of positive charge on the cylinder, on the sphere. You'll see that we didn't show the positive negative pairs that don't balance out. So for example, in the middle diagram, we had 1, 2, 3, 4, 5, 6, 7 pluses and 2 minuses. 2 of the pluses get paired with 2 of the minuses to be neutral, and the other 5 pluses are represented right here. The negative rod itself does not change. The negative rod doesn't add electrons or lose electrons in the process. So charge by induction produces unlike charging. The rod started out as negative, the sphere ends up as positive. They're opposites. And it requires an electrical ground, either a wire connecting it to ground or somebody touching it. Okay, moving right along. Let's look at conductors in electrostatic equilibrium. So, if you are in electrostatic equilibrium, the charges are not moving, and the charges are as far apart from each other as they can get. So the conductor is going to have an electric field of equal to 0 inside of it. If it were not 0, the charges would have to move to balance it out. So at rest, they're standing still, the field inside is 0. All of the net charge, all of the unbalanced charge will be on the outside surface of the object. And the reason for that is the outside surface is going to give the maximum surface area, so the charges can get a maximum distance apart. And then last, the conductor, when it is charged, will have an electric field just outside of it. It's going to be perpendicular to the conductor. So those electric fields are always perpendicular to the conductor's surface. Let's look at another example real quick. This is a sort of simple version of what's called Faraday's ice pail. So if you have a metal container, that's what this represents, and hollow on the inside. So this nested set of circles would represent the walls of a container, hollow in the middle. And you put a +4 positive charge suspended in the middle of your container, in the hollow spot. It would attract negative electrons, and that would leave the outside surface with a +4 charge on it, because the electrons that started out balancing those positives are being pulled towards the center surface as they seek to get as close as possible to that positive charge. So on these scenarios, it's always going to be, if you have a charge suspended in the middle, that's going to equal the charge that's induced on the outside edge. When you take the charge in the middle and you make it go away, you pull it out, all the charges will redistribute, everything goes back the way it started with 0 net charge. Now I'll admit my diagram's not a very good diagram, so we will look at a different one. So on this diagram, you can see we have our little metal bucket on an insulating stand. So we can take our charged object, you can see it's positively charged. And if we drop it inside the metal bucket, the charge ball going to be put inside the metal bucket. We're not going to let it touch anything. We're just going to drop it inside. Then the free negative charges will be pulled towards the inside. Our bucket has a lid on it. So the free negative charges will try to get as close as they can to the positive ball. That's what these are. And that means that their positives are going to be on the outside surface. So if the ball has a +8 charge, the surface will have a +8 charge. If the ball had a +27 charge, the outside surface will have a +27 charge. If you let the ball touch, because the ball started out positive, it's actually going to accept negative charges, and you'll end up with the bucket itself ending up with actually a true net charge on it. All right, so we're going to stop here and we'll pick up with our next video with some numeric examples.